Okay, so last time we talked about exponentials. Today we're going to move into logs, give you a quick review of the exponentials. When we did problems like y equals 2 to the power of x, we talked about graphing those. So you can plug in points. If I plug in 0, 2 to the 0 is 1. If I plug in 1, 2 to the first is 2. So you can quickly on a graph go ahead and do 0, 1, 1, 2. We know that your basic exponential has your asymptote at y equals 0, and then you can draw your curve coming off of that, right? Today when we talk about logarithms are inverse functions. Because this is a one-to-one function, remember one-to-one means it passes the horizontal and the vertical line test. It has an inverse, and its inverse function is going to be the log. So when you talk about exponentials, and you talk about logs, it's going to be something like log base 2 of x equals y. Log base 2 of y equals x. Remember what you do is if this is log base 2, 2 becomes your base in your exponential, so it's 2 to the x equals y. So this function right here and this one are the exact same equation. If you wanted to find one or the other, you switch your x's and y's, and then we solve using the properties we're going to talk about in a minute. When you go to graph this, it graphs the inverse. Remember, your inverse is when we take over the line y equals x. So the inverse function would be, instead of having your asymptote here at y equals 0, we'll have a vertical asymptote at x equals 0. Instead of hitting at your y-intercept 0, 1, you're going to hit your x-intercept 1, 0. And then your graph's going to curve off of that. So our exponentials have a horizontal asymptote. Our logarithms have a vertical asymptote. And you can do your points off of that. Sorry, the reason I'm not here today. All right, so let's move into more logs. All right, so this is just reminding you it's a one-to-one function. It has an inverse. You can flip those values. When we're talking about logs, your basic log is going to be log base 10. So I showed you an example of a log base 2, but you can have, if it's written a plain old log, if it just looks like this, log of x, that's automatically log base 10. That's the one that's going to be in your calculator. So if it's a plain old log or it says log base 10, you can plug that in your calculator to find your answers. Anything other than that, log base 3, log base 5, log base anything else, you're going to have to use the properties to solve that through. All right, here are a bunch of the properties. You can take a second and pause the video and write them down in your notes. Okay. All this is doing is showing us if you take, for example, and you switch this over to the exponential, a to the 1 equals a. Well, that's obvious, right? A to the x equals a to the x, things like that. The key is that when we go to solve, understand that base a and log a cancel each other out, and that's how you're left with the x. Or over here, log a and base a cancel out, and you're left with just the x. We'll use that in solving. All right, so here's an example we go through and solve. If you're looking at number 1, what I would do is say, hey, both sides have log base 2. I can raise both sides to a power with a base of 2. So 2 to the power of log 2x equals 2 to the power of log 2, 3. The base 2 and the log 2 cancel, leaving me with x. Base 2, log 2 cancel, leaving me with 3. Your answer is x equals 3. Easy enough, right? Here, log 4 of 4 cancel. That leaves you with just 1. 1 equals x. Easy enough as well. Again, this is that same concept of you could switch it to the exponential. 4 to the power of x equals 4. What does x have to be? It's got to be 1. All right, so simplifying here, same concept, log base 5 of 5, and log base 7 to the log of 7. Those things just cancel out. The top one is x, the bottom one is 14. They're talking here about finding the inverse. So again, like I said before, you can switch the x and y's. You can use then the properties. So what I would do is, if I switched, here's your log function, switch your x and y values so you can find the inverse, and then use your properties. How do I get rid of log base 2? Raise it to a power with a base of 2. So these cancel, leaving you with y, and on the side you have 2 to the x. So that's our switching rule that you guys know. So here are a couple of trying to solve them. So when you're going through and you're trying to solve them out, again, the first thing we want to do is switch x and y. So we've got x equals 2 plus log base 10 of y. Now I'm solving for y. I'll move my 2 over first, so x minus 2. And then how do you get rid of log base 10? A base of 10. So raise everything to a power with a base of 10. Those cancel, and you get that 10 to the power of x minus 2 equals y. Okay? Same concept here. Switch my x and my y. So here's my x, here's my y. On this one, the first thing I want to do is that base 10. Because now this one is inside the function. So you have to get rid of the log before you can move anything inside the function. Cancel your 10s. 10 to the x now equals y plus 1. Now you can minus your 1 over. 10 to the x minus 1. Now this minus 1 is on the outside. It's not in the exponent. Equals your y. This is an example of doing the graphs. Like I said, you can think of it as an exponential. Find the 2 points. Flip it over that line, y equals x. So this is that exponential version, and this is the log version. Okay, here's another example. Going through and plugging in some points. So you could plug in 1 for x, plug in 5 for x, plug in numbers that make sense that you can come up with the answers. So set up that table. Sorry about that. So from the graph, we can look at it and decide that this is a domain. I think that graph shifted a little bit. It's 1, 0. These are very close to the line. They're not actually touching the line. So we've got a domain. Sorry about that. Okay, so we've got domain is going to be all reals greater than 0, right? Because we're going to have 0 as an asymptote here. These aren't actually touching the line. Your range is going to be all reals because it's going to go on forever up and down. So this is going to be reals greater than 0. This is going to be all reals. Your x-intercept now is at 1, 0. That's that specialty point. And it is an increasing graph as you can see it going up. Transformations in logs work the same as transformations in everything else, right? So if I have minus 1 on the inside, it's shifting to the right one. If I have plus 2 on the outside, it's shifting up 2. If you put a negative inside, it's going to flip it horizontally. Negative outside is flipping it vertically. And any number right in front of the log multiplied to the log is going to be your stretch or compression factor. We talked last time about your natural base e, and then you have its counterpart, the natural log. So ln is what we call our natural log. It cancels out the e. So this is like saying log base e of e. They cancel out, you get 1, right? So take a second and write some of those properties in. And then trying to solve some of those out, the top one is natural log of 1 over e. We'll move on to this one because you can see this one. So again, this is e. ln is like log base e. So if I think of it as e log base e of 5, e and the log e cancel out, your answer is just 5. So know that E and ln cancel. Concept here, same thing here. If you have the natural log of E, they cancel out, your answer is just 0. And here when they cancel out, you have that invisible 1 left over. So on this would be an example of one that you're graphing, right? Again, natural log is going to work the same way. This one's going to shift to the right too. This would be something that's flipped horizontally and shifted to the left too. You could go through and graph those by 1 point at a time and then see what happens as you look at the domains.